and welcome everyone here who's not already familiar with the Skyscraper Museum. Gee, I thought I would, can somebody give me the next slide, or am I just going to click this? Nobody taught me how to use there we go. The Skyscraper Museum and our current exhibition, which is called China Prophecy, Shanghai. And this lecture series, I was going to hold up the card that you got inside of your program, and the location of the Skyscraper Museum is on the back, marked with our logo in Lower Manhattan. So if you haven't been there already, this is a preview of what the exhibition looks like, and I certainly invite you there downtown in order to see the show anytime from Wednesday through Sunday from noon to 6. And we are so pleased tonight to be in the second of the series of Shanghai Skyline, and I hope you all received this brochure as well. And with this partnership with the Asia Society, and for the next 3 programs, which will all be held at Baruch College at the new campus, the vertical campus, as is appropriately called for the Skyscraper Museum, at Lexington and 24th Street. So we've been around town with this series, and we're really delighted to be able to bring in students as well as new audiences. But for those of you who aren't familiar with the museum, the Skyscraper Museum, I'm the founder, director, and curator. 11 years ago, going on 12 years ago now, we started the museum in vacant available space in Lower Manhattan in a series of locations that were old bank branches. But for the last 5 years, we've had this gorgeous permanent home in Battery Park City, designed by SOM, and one of our evening's architects about Shanghai will be the team from SOM that will speak on November 10th. So this series and the exhibition, which is the third of 3 shows that explored the idea of Future City 2021. Future City 20 was New York Modern, the first exhibition that looked at visions, American visions of the city of the future that saw New York as the prediction of the world to come, the skyscraper, the city of towers for the 20th century. And then bridging the 20th and the 21st century was Hong Kong, and we looked at the show called Vertical Cities, Hong Kong, New York. That's from our conference. That's the brochure from our conference last October. And we'll be having another one in Hong Kong this coming January on vertical density. And then the third is the current one, which will be up through March, the China Prophecy Shanghai. And when we looked at the idea of what would be the city of the future comparable to New York in the early 20th century, and with this wonderful cartoon from December 31st, 1899, predicting as the first skyscrapers were rising in Lower Manhattan and up around a little bit around Times Square, but especially downtown, the idea that the city would just grow beyond control with this incredible energy predicted what did happen in New York, but it also happens on a much faster pace in the city of Shanghai. So when we thought about what would be the city of the future for the 21st century, it was natural that we would train our focus on Shanghai. So this evening I'm going to introduce, let's just leave that. Introduce the 3 speakers, probably one at a time. First, Jun Xia, who's the architect for the Shanghai Tower. And then the structural engineer, Dennis Poon from Thornton Tomasetti. Jun Xia is from the architectural firm Gensler. And the third of the speakers is the MEP engineer for the project, who's Doug Moss of Cosentini. It's interesting, these are all New York-based firms. Jun heads the Shanghai office for Gensler, and each one of these firms has multiple offices in international capitals. But they are also New York-based, and to a very great extent, the skyscraper is an American export. Our next speaker next week, next Tuesday at Baruch, will be 2 of the partners from KPF, Cohn Pedersen Fox. In fact, Bill Pedersen, one of the principal founders of that firm, New York-based, and also Jamie Von Klemper, one of the younger partners who does a lot of the Asian work. They do a tremendous amount of work in Asia, and as does SOM with the Shanghai Jinmao Tower and the structural engineering which they do in-house. So this really is an American export, and we're fortunate with the exhibition and with this series that we can draw on our local talent here in New York. But I do want to especially welcome tonight Jun Sha, and I'll introduce him to you now, and then as we move on to the different speakers, maybe I'll just come up, Dennis, and briefly introduce you before you start to speak, and likewise with Doug. But Jun is the design director of the Shanghai office of Gensler. He has completed many high-profile projects both in China and in the U.S. Born and raised in Shanghai, Jun Sha holds a bachelor's degree in design from Tongji University in Shanghai, leading university, and a master's of architecture in urban design from the University of Colorado in Denver. In Beijing, Jun Sha began his career with the Chinese Academy of Urban Planning and Design, where he was involved in master planning and architectural design of housing, retail, and office buildings across China. After joining Gensler in 1991, he was appointed principal in 1999 and became design director of the Shanghai office in 2004. So Jun is going to take about 25 minutes in order to introduce you to this design for the Shanghai Tower, which was won by Gensler in a competition after a series of competitions by leading international firms like SOM, KPF, Foster & Partners, Caesar Pelli, Clark Pelli. But Gensler prevailed just in June 2008, and the project that you're going to see now is beginning construction at the foundation phase. But Jun is going to introduce you to the design concept and inspire you, I'm sure, as he did when he showed me this project with the vision that it represents for a greater Chinese future for environmental design as well as architectural design. Jun?
Good evening. It's a great honor to be here in the great city of New York. And I was here in 1989 and was interviewed with IMPE office and SOM office, and I was offered both jobs from both offices. But eventually I turned back to Denver because I was working on great opportunity to work on Denver International Airport at that time, and that was one of the largest airports in the world at that time. So it's great to be back in the skyscraper city in New York, and I really admire Carol's passion and the dedication for the skyscrapers. I think it's a great human phenomenon that we're living in a world today, particularly in China, that we're doing great buildings over there. How do I do this? Hit this? Great. First of all, let me talk about our firm briefly. Gensler is a multinational firm, and we have office here down Americas Avenue and the 6th Avenue in New York. And we have 36 offices right now globally, and our headquarters in San Francisco. And we are currently in China. We have about 120 people, and we're doing multi-function architecture, master planning, and urban design and interior designs are multi-service over there. This picture as a rendering presents where the location we call the New Shanghai or the Pudong area. I don't know if anybody are familiar with Shanghai, the geographic nature of Shanghai, and the is there a laser point here? Anyway? Oh, I'm sorry. Can I go back? Yeah. So the site was surrounded by a river called Huangpu River, which is meanderings around, and which is where the motherhood of Shanghai. Great, thank you very much. So this is the Huangpu River. This area we call the Bund. The Bund was developed by the turn of the last century. British is colonized by British mainly, and the Germany and the French men, and part of a little bit of the United States and Japan down in this side. But this is where they call the Bund. There's lots of historical buildings where the banking and the hotels and was formed. This area, about 20 years ago, is entire wheat field. So this side here, across the river, we call it Pudong. Dong means east. The east of the river is the new development area. Started developing in 1993, and they had international master competitions, and 8 international architects engaged, and eventually they have a local design planning firm to collect all the ideas to combine to make a new planning district. We call it Pudong Specific Economic Zone Development. There's lots of tax benefits there, so they can attract many investment and for tax-free for like 50 years, any investment on this piece of land. That's why there's lots of development since 1993. In the planning, in this very planning, they planned 3 very tall buildings together, to compose very unique skyline for Shanghai, which never have been done in the other place in the world. The Shanghai Tower, which was built around about 10 years ago, is done by Skidmore and owned by the Finance Ministry of China. So the government owned this building, and there's a Grand Hyatt Hotel and the office buildings down below. So that building is about 400 meters tall. The Mori building was owned by Mori Group of Japan and is designed by KPF. It's about 490 meters tall. So it's about 100 meters taller than this building, which is just recently completed. And Park Hyatt Hotel with office building down below and with observation deck and a 101 floor. So the third building is the Shanghai Center. So the Shanghai Chinese government decided to develop this very site at this moment for a couple of reasons. Number one is China, they want to show the world the confidence about arriving to the international community, arriving the contemporary modern time, our aspirations to build a tall building, not only as tall, but as more about quality, the sustainability, and the willingness in the economic downturn to take a great leap forward. So this building, under planning, is scheduled at the top floor is up at 580 meters tall onto the slab. And then with the structure above, put a design, and per our scheme, Gensler scheme, the top tip is at 632 meters. The building is a part of a kind of a government investment. Part of it is really important completion of Pudong as a world finance center. So most of the function of the building, I will introduce you guys a little later, is really about a financial tenant, like here in Manhattan. The 3 buildings together, we really think composed a representative of China's past, present, and the future. So I'm going to use this video to show you guys. I don't know how, is that sound? Well, Leah, is sound working? Okay, good. So the film is show you a little bit about the overall, the scheme of the building, give you a little bit of kind of a idea about all the components and the relationship to the city and the view from different parts of the city. This is a very famous bridge across we call it Waibai Duqiao. It's a very famous bridge to link the Shanghai from north to south. I'm looking at it from Suzhou Creek, from Puxi to the Pudong. This is from old city to the new city. Most of this side is the residential side, the high-end residential side. The top of a building turbines at a 600 meter tall. There's a wind speed at 4 meters per second. So the wind turbines generate enough energy to power the entire architectural lighting and also the observation tower. The hotel lobby is at the same height as the observation tower at the 101 floor. So it's going to be the tallest hotel lobby in the world at the time. The building is divided by 9 different vertical communities. So we call it a vertical city. So that's how the tall building we think in the future will work. We talk about the past, the present, and future. The Jingmao Tower is very much like a Chinese traditional pagoda. It represents the Chinese past. And the Mori building on the other side is more about faster growth Chinese economy of today. And we believe this tower should be represent as like a youngest brother in the family, should represent the future of China. Those are the sky lobbies. So these are the hotel level, you can looking out. On those areas, those are all various bank headquarters buildings. HSBC, Bank of China, Industrial Commerce Bank of China. So it's all bank headquarters around this area. On the podium, there's retail and entertainment and cultural facilities. And we particularly introduce a cultural, engage the cultural elements into the building. So there are lots of meaningful events representing the China and what's going on in the world. And so there's like a 2,000 seats, a multi-function room. Eventually we have a multicultural and functions in the projects. So the night view, this will be lighting feature will be a green feature. Basically, will be reacting to temperature and the weather and the wind of nature. So the light will change its color and intensities during the night. So now I'm going to talk about a little bit about from how the building is fit in the site and particularly with 3 buildings together, how wide we choose the form it is and how they're working together. So this is the site we'll be looking at from a bird's eye view. This is the Jingmao building. This is we call it Shanghai Central Avenue Boulevard. It's a main street. It's a main avenue that connects entire Lujiazui financial district. It's a free trade zone at that time. So anybody coming to here have very tax benefit, like I just said. So the 3 buildings, Jingmao Tower is the first built, and the second one is Mori building and just being built. And our site, so it's basically is a triangular relationship of 3 buildings. And like we just talked about, the 3 buildings, Jingmao Tower, the form of it represents Chinese pagoda, tower pagoda. So it's a very traditional, but in a modern way. The Mori building is a very sculptural and a very sharp-edged and a very dynamic that form of China growth and a fast economy. And this building, when we enter the competition, so a couple of things we came into our mind and we decided to do. Number one is we think that this building needs to be working together as a family. In Chinese Oriental thinking, a family is important than individuals. So as 3 buildings together, we think the building need to be part of family, but it's going to be youngest brother. Or it'd be a little different because it's the tallest one. So on the other hand, we also determined this building need to be asymmetric, because being the tallest building in Shanghai as a city, Shanghai is a very, very asymmetric city. Unlike Manhattan, it's very grid. And Shanghai is the streets like Boston. It's a very organic streets, so you can view the building from very different angles in the cities. You guys can see this is the real picture of the city. So people can, because the rivers, it's very organic, goes through the city, and this Suju Creek goes through the city. So north, south, east, west, the viewing from these central towers be very different. So being asymmetric, we think, is important. And in the end, we decided the building is being spiral. Spiral does a couple of things. Number one, spiral form ties three buildings together as a very dynamic ways. It's not confrontational. It has some kind of dialect with the other two, but also is most futuristic looking. And there's other reasons why we're doing that. From the height standpoint, 432, 492, and 632. So the harmony of this form comes with from three building ratio. The line is very naturally goes up and toward the sky. So it's not a very static way of how the building progresses with three buildings together. The zoning building, and we talk about the vertical city. And the vertical city, the concept that comes with how can we make a tall building is not just one building. When the building gets that tall, this about entire area is about, I would say, is 500,000 square meters. 500,000 square meters is 5 million square feet. Entire building with a basement and a tower. So it's like a small city. So the zoning of the building is from the operational standpoint, from a structural standpoint. My partner, Dennis Poon, will talk about it. And from a mechanical standpoint, and my mechanical partner, Doug Mass, will talk about. And also from human aspect. So each zone will be treated as if an urban block, as a block. So you have the distribute the service amenities from each, we call it Sky Gardens concept. So the building, the block outside of the block is wrapped around this like the city envelope of this glass curvilinear spiral glass curtain, serve as a buffer between outside space and inside space, which is very oriental. In China, we always think that between black and white, there's a gray. The gray is very important. The space in between, inside and outside, in between is very important. If you go to any Chinese garden architecture, before you go into the real important space, there's always in-between space, transition space. So the building, in a very, very elegant way, wrap around like a skin and like a silk around, there's in-between space between outside and inside, which also is a green concept. So the building is divided by 9 zones. So the zone 1 is the lobbies, the hotel functions, the public amenities, retails. Zone 2 to 6 is the office. And each zone will have different kind of a floor plate size, which will fit the different tenant needs. Some of the tenants probably need a big floor place, range from 4,500 square meter to 2,000 square meters. So there'll be 2,000 square meters. So it'll be different tenant. We have different conditioned floor plate zones. And zone 7 and zone 8 will be the hotel. The hotel lobby is in the middle. So above will be luxury hotel suites. Below will be luxury business hotel suites. The top zone 9 will be exhibition space and observation space. Also contains the wind turbines for wind engineering elements. So the program, because it's conference and retail, office, hotel, and observation, and the boutique offices. And we preserve some of the office suites on top is for the potential, the exchange space or the showcase space for Chinese top companies, for them to, as a place to engage the world, and as a place they can meet the people from around the world, show their business, and make very important relationships. In China, they're making private relationships, the clubs, all those stuff is very important as a business function, but also can be very public, can be as a company's window engaging to the society as well. Again, go back to the form. I talk about the form we talk about from an urban design context. We said there's three buildings working together. So this building being the very futuristic looking in a spiral. Three buildings together, the building spirals 120 degrees, which is exact 1/3 of a circle. So it's actually is a metaphor about harmonized three buildings together as a triangle relationship. But everything works not only for a metaphor, for a reason, but a symbolic reason, but also as a very important engineering reason. For a tall building like that, the wing engineering is the most important thing. And the architecture form needs to work with the force of nature. It's very important. So the spiral, we studied from 90 degrees, 110 degrees, 120 degrees, 130 degrees, 150 degrees, and 180 degrees. So in the process, we studied a different rotation in the spiral. And we put them into internal testing to see how the spiral shape will affect the wind engineering. And the result tells us the more spiral helps, the more, am I okay with time? Helps reduce more wind resistance. So it actually helps our structure system much better, helps my friend, Dennis, much better here. But also, we want to have the form itself make sense to working with the functional space inside. So make sure it's very efficient, make the internal space work, and also the looks not too much movement. So it's a very subtle, elegant shape. So eventually, what we picked is 120 degrees. We go back to the big story. We said that this form is futuristic because the spiral shape is from the physical standpoint, from the smallest things of our nature, electron, to the biggest thing, our universe. It's our existence is surrounding the spiral, nature of a spiral. So that's why we think the form is very represent the future and the nature as well. So the rotation, 90, 120, 150, 180. So 120 degree spiral is about 1/3 of a circle. Actually, it completes the three building together relationship. We think it's very nicely. And the other things we did is a scaling. Our curtain wall is very challenging design because the glass form not only rotates, but also tapers up above. So we tapers and rotate at the same time. So we have a very strong, very big challenge about designing a curtain wall system because the glass need to be very uniform. It also be practical to make the glass work. Those are two things, both spiral and rotation and scaling, help us the wing engineering. We studied about the form with our shape, this scale our spiral and the scale shape of this rotation shape, compared to regular rectangular tapering box. Let's say if we take a John Hancock building form, the same form project it to 600 meters tall, our form will reduce about 24% of a wind resistance from a structural load. So the floors. So this is a typical floor at level 22, which is one of the amenity floor. So you can see the entire floor engages with outside the ring. And inside the ring is actually is our usable space. But on these amenity floors, we can have the retail sky gardens with retail surrounded, as if you have on a street block in a corner you have bakeries, coffee shops, and retail banks to serve the communities. This is your typical functional floor, which is detached from the outside the spiral. This glass skins, a very simple central core, and a very functional space around it. Hotel floor. So the building, the ring is smaller, still triangular on the outside. So this notch is from here to here already. So this is a hotel, typical hotel rooms. The core becomes smaller because our structure design is brilliant. On top we have smaller floor plate, have smaller core.
So we have very usable floor areas, very efficient floor areas. The client, although it's owned by government, but they are very, very stingy on us to create a very efficient, a very great business. So doing tall building not only for aspiration of being tall, but also need to be very efficient at business. So it need to be very efficient floor plate. It need to be good business. So on the 118 level is our luxury hotel suites. The hotel lobby is on the 110 here. Down here, there will be a spa and restaurants. Here will be our reception lobbies and the cafeterias and the club lounge area. So these are the Sky Gardens. Sky Gardens, so those are the big, so every atrium space, we call the block, every zone, atrium space, about 69 meter tall, which is every 15 floors. Part of the reason is a fire protection. According to Chinese architecture code, every 15 floors, you have to have a refugee area for temporarily for people to, in case of emergency of fire, the people can temporarily be in that place when the fire is being dealt with. So every 15 floors, we have a sky lobby, and down below is a refugee floor, the structure floors, and the mechanical floors. Our partners will talk about this a little later. So this is Sky Gardens, and we have this ring here. We have sprinkler system actually to help for the fire safety issue here. So the sprinkler system will be here around this element here, but also as a lighting element. It's very difficult for Chinese fire department to accept the Sky Garden design because of the open area, because of protection of the smoke and the fire. So this is one of a big accomplishment to get them to approve. And we also visited the New York Fire Department to exchange ideas how they think the tall building or fire protection safety issues were working in the tall building like that. So it's a great conversation with them. This part of so the curtain wall outside, we call it like a silk wrap around the body. Actually, the building's glass is very, 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 very thin. Our structure engineer and the curtain wall engineer working together to create a very, very light structure system. So actually, the glass is being suspended between amenity floors and horizontally be supported by those spots, those structure elements like a 40 centimeter in diameter to support from each floors. So it's a very, very like a bicycle ring, like a bicycle rings. So you can be very transparent, visually transparent, see the outside views. So one of the ideas to create a sky garden, actually, I like to talk about it, is like create a buffer between the outside air and the inside air. As a part of we're working with Dennis and our Constantini mechanical engineer to create a kind of a atrium buffer. So in the winter times, so this buffer to keep the building warm, and the summer times keep the building cool. So be a kind of heat and the energy kind of exchange space. So to really to save the energy for the entire building. So it also works as a green concept, not only as an architecture feature only. So those are kind of when we did the competition together. I remember then that Doug Mass went to present our goals, how the building can be the most sustainable building. And this building, we are designed to the LEED Gold category for American standard, but also designed to China Construction Ministry's China 3-star green, which is the highest grade of energy green standard as well. So those are kind of the goals we try to be. Actually, we are implementing and try to achieve in these buildings as the most sustainable high-rise building in the future in the world as well. And that our client has made a commitment, although there's a lot of upfront investment, but they think that the building will last for 100 years. So those are important for them to commit to that. Those are some just the basic numbers. These are the central park of this Lujiazhu area. So the carbon reduction of this, that's what the picture actually Doug Mass showed in our competition, which is a very good illustration about how green statistically we can help to accomplish for our buildings. Water, there's a lake here, and there's how much water savings from our buildings. And in the end, I think my time is up, and I think the key is, I think I want everybody understands that China now, the client itself, as a society, as a client, a group of clients, they have become very, very sophisticated. I know Carol, when they had to talk to them, when they started this development, they only see tall building as a symbol of modernization. Today, they treat the building is not only as a metaphor to them as China's arrived anymore, but also as a good business, as a good investment. The reason why they have to build a tall building is that because of land value. Leah in our office today, she wants me to talk about why Shanghai needs to build so many tall buildings today. Because the land value they created through the last 20 years on this land, actually, originally the building does not have that much volume. But today, when they assessed the investment and the land value, they decide the market determines they need to build that much volume and that tall of a building to appreciate the land value what they have. Also, the land is always owned by Chinese government, so it's not private-owned land. So that's why the tall building and to utilize the land to make some of the land value is very important to them. So they really treat it as a very important business. So when we design, the part of the high American architects design for them is we knows how to do building as a business, not only just a beautiful sculpture only. So that's part of the reason we are able to actually win the competitions together with my partner. I give my partner Dennis Poon talk about structure, and later on Doug Mess from Constantine talk about mechanical. They all made great contributions. A building like that has to be a collaborative, a team working together. So we have about 40 consultants and our team together. So they are just two of them, but this building is a great example for a tall building today. Have to be a bunch of people working together and to share the wisdom and knowledge and the process. So here I'm going to Dennis Poon.
Thank you so much, June. I'm just going to very quickly introduce Dennis Poon, who's the managing director at Thornton Tomasetti, based here in New York. And I think I first met Dennis about 10 years ago when he was working on the then world's tallest buildings, which would have been the Petronas Towers in Kuala Lumpur. And since then, he's successfully worked on just about every one. The Taipei 101 worked on the structural engineering there in Taiwan. He has, as you can see, this is a very tall building, so he is specialized in super talls. The Burj Dubai, of course, in Dubai at 818 meters is about 1,000 feet taller than anything else. But if you look at the person who has been in charge of the most super talls around the world, including some that are on the boards now in Korea, and just about everywhere you look, Dennis is in charge of those projects. So let me just quickly go on to Dennis so that he can wow you with his with both his experience and expertise apropos to this very tall building, which will be the world's second tallest building if it beats some of the others that he's currently in the process of designing now.
Carol, thank you for the nice remark. I think probably I fall in love with tall buildings because I'm short myself. So the only way to make it tall is to work on tall buildings. However, I think I've been extremely lucky that I have the great opportunities working with the top architects in the world and the good colleagues of mine like Constantini and other engineers in the team to work on exciting projects like that. As Sergeant of Gangster put it this way, he mentioned the past, the present, and the future. Let me share some experience with you about the past. We started the design process with Sergeant and his team in Shanghai more than 1.5 years ago. And the design competition has been a long process. and it lasts more than 6 months. And I want to express to you how many evenings we have been working through to modify the buildings, the form that Sergeant mentioned. The product you see now is going through months and months of work and fine-tuning. And we have several job interviews and presentation to the owner. And one of the last interview, I was quite surprised. When we all walk in as a team with other 9 competitors, everyone, when I walk in, I saw our competitors hauling in beautiful models. Each one is bigger than us, with more lighting than us. And I look at Sergeant, is it what we got, just a tiny model? That is quite scary. But we're competing against top architects in the world. And finally, we pulled through, and we won this project with a good teamwork. Let me see how to work on this one. Thornton Thomas City is a structural engineering firm headquartered in New York City with about 700 engineers worldwide. And we basically have about 15 offices around the world. We also have office in Shanghai, working closely with Sergeant's office in Hong Kong, Shenzhen, also in New York and California and Chicago, and also in Middle East. We are basically involved in many projects around the world, not only super tall buildings, but also arenas, stadiums, and hospital, hotels, etc. We also do houses in addition to that. We did the Hampstead residence many years ago. I just want to thank my teammates who have been working much harder than me, and some of them are here today to share the experience. I try to make it quick because Sergeant have covered most of it, and I want to start with something about this project. When we were assigned this project, we were facing with different challenges. First of all, the building is very tall. It will be one of the tallest buildings in the world, standing almost 2,000 feet, almost 50 stories taller than the Shanghai International Center. And that's one of the challenges, being tall. And secondly, Shanghai is quite windy. We have to withstand a typhoon wind load up to almost 112 miles per hour, and with gust wind much higher than that. And equivalently, we almost have to stand more than 100 pounds per square foot of wind load. That's another challenge. The other one is earthquake. Shanghai is an active earthquake zone. What makes it worse is also the soil situation. The soil is, because it's situated at the delta area of the river, they never find rock in Shanghai. They have never seen rock, so it's good for your cars. But even if people gone down to half a mile deep, they couldn't through borings, they couldn't find rock. And they only have silty clay and sandy clay, so it's very compressible material, and it will resonate the earthquake and magnify the earthquake forces pretty bad. So if you have a smaller earthquake, you will get a huge magnification there. And also we're dealing with liquefaction, because the water table in Shanghai is about 3 feet below grade. So if you dig a whole 3 feet, you will see water. You will have a natural water, drinking water underneath you. So it's another challenge. So bad soil, and also we're dealing with a settlement, because with bad soil, with this heavy building or tall building with the weight accumulated, we cannot afford to have uneven settlement. Otherwise, we have the Pisa Tower. So we have to be very careful about it. So dealing with the challenge, and on top of that, the owner comes, well, your fee is too high. No, that's not that, but I have the requirements for you. We want this building to be safe. I say, how safe? He said, very, very safe, because it's a government building. Okay, fine, no problem. We will do it for you. Then, but I want it to be cheap too. So how cheap? He said, very economical. You cannot be more expensive than the other 2 buildings. Okay. At the same time, how efficient? We want to have a lot of interior space without killing my valuable real estate. That's another requirement. And what else, sir? They say, I want it to be simple to build, because I want to build it very fast, faster than the other 2. So those are the requirements, and go to work. That's why we also have a rush schedule. And so those are the requirements. With this in mind, you understand that this building has a tapering form, and how do we make it simple? And the building is twisting, so we cannot do formwork twisting. So working with Sergeant and his team, months and months, we come up with some tricks and ideas how to keep the structure simple and to fulfill the requirement. Look at the size of the site. This is the entire site, the entire city block. And this is the base of the tower, and that is the podium area. It's good to be a Chinese worker because you live on site. You don't have to commute. And they don't have the special union rules. And they have a canteen here as well if you want. Now, look, give you some sense of scale about this building. This is the tower, almost 2,000 feet. And right now, Burj Dubai is the tallest building in the world. And Taipei 101 is about 508 meters. And Jingmao is about this is Petronas Tower. So this is going to be one of the tallest buildings. These are not being built yet, but this is real. So give you some sense. It will be one of the tallest buildings in the world. Again, you can see that the different zones Sergeant has covered. We separate into 9 zones, but if you look at the floor plate, the floor plate has a diameter of 74 meters, 76 meters, 70 meters. The circumference of the floor plate is getting smaller and smaller. So if we build a building from a 46 meter diameter to a 50 meter diameter, it will require a huge transfer, like staggering up. That will be highly uneconomical. We'll get fired. So basically, we have to work with Sergeant and say, we work out with this magic number so we can eliminate transferring every zone by another transfer system. So it is a lot of tedious collaboration with the designer to come up with dimensions so we can have a sloping column in a way that the column can go straight up and down and sloping in a shape that fits into the profile and the form of the architecture. That's one of the direction we conquer the simplicity. I'll go on further to test to get you another one. Okay, the gravity system. Okay, now this is our computer model of the entire structure, and including the curtain wall support structure above. Now I'll give you a short movie. We should have some music, right? You can see that this is the perimeter grid that supports the glass curtain wall, which is hung almost every 14 floors in each zone. And we have an atrium space in between each zone, it's called the sky lobby. And this is the mechanical floor. They have a full triangular plate size that will extend to the full perimeter. The building is a steel building with steel floor framings, steel deck, metal floor, and concrete slab on metal deck. The concrete core, okay, I will let it finish first. What you don't see is the hanging steel rods coming down from the mechanical floor, 14-story up and down to support all this glass curtain wall that form the atrium space in between. The crown is not there yet because we're still making final adjustment. So the core is primary composite. Let me jump into it. Basically, the building consists of a main concrete core. The core itself is about 30 meter by 30 meter, which we try to make it consistent throughout the building. And we choose this core because we think that it's sturdy, it is very fire resistant, and it gives a lot of mass, to give a lot of stiffness to the building. And in China, labor is cheaper than the United States, and concrete material is more economical as part of the owner's requirement to be economical. And it fits well with the construction schedule as well. But inside the core, we have steel columns buried inside with a lot of rebars buried inside to make it safe. Now, outside the core, how do we make it simple is on each side of the core, we have two super columns on each side. So this building in the east-west direction, we have two super columns and two super columns. In the north-south, we also have the two super columns. And these are the miscellaneous corner columns. This super column ranges in size of about 5.5 meter by 3.5 meter at the base to 2.2 meter by 2 meter at the top. And this build-up column consists of steel wide flange build-up plates and reinforcement with high-strength concrete. That is also quite labor-intensive, but it's also manageable in China because of we take advantage of a more reasonable labor cost there. And it's also quite sturdy and fire-resistant. Look at it's all encased in concrete, so we can eliminate fire. It's quite sturdy that we can take a lot of impact. Now, we have the super column. Now, how do we make the building safe against the wind load and the earthquake? The primary system is like skiing. For low-rise building, we only have a tower core itself like the trunk of your body, and you can withstand the wind load. But when the building gets up to 2,000 feet tall, the body itself, the 30 meter by 30 meter core, is not stiff enough to withstand this lateral motion. So we took like the same theory or the phenomenon of a ski post. So we call it an outrigger system. That is like, imagine you're the body, people give you a pair of skiing posts, and your hands, you stretch out with your hand, is your outrigger trusses. And when you holding two super columns on each side of your hand, connecting the core, it gives you a more stability turnover base. So when you twist like that, the building is gaining more stability. Can you imagine you stand like that? It's less stable. When you do like that with two super columns standing, it will be much more stable. That's how we achieve simplicity and stability for such a super tall building. And we hide these outrigger posts every 14 floors within the mechanical zone to work with Douglas Mass of Constantini, that we will free up all the space for the office. That's how we achieve efficiency for the architect and the owner's requirement. And we call it the outrigger truss. I'm sure there will be good engineers in this hall who understand it very well. This has been quite efficient, but for earthquake, okay, it's not enough. Because in earthquake, when the building shakes, we also want ductility, like more elastic. And we also want to have a second system of defense. So the way to do it is we put a ring of bell truss, also 2-story deep, in the mechanical floor every 14 story, and this will form a mega frame. The frame is like, this is the leg of your table. Imagine these are the legs of the table, and this is the top of your table, rigidly connected, and you try to push this table. It will give you another rigidity by using this ring. We call it this is a frame. So together with a frame, we enhance the structural safety of the building. So we can tell the owner, this building is very safe. Now, we also take advantage of the form to support the curtain wall. Every 14-story each zone, we cantilever out some trusses. And these are the trusses that we start hanging all the steel rods to support the ring on each floor for the curtain wall. We call it the radial truss. So we try to fit in all the components like a Swiss watch to make it work. We call it the radial truss system. Now, this is the composite picture. So this is the mechanical floor. We have the outrigger trusses. We have the radial truss. And this is the floor. Okay. Don't forget, all the office space remain in a circular shape. The building itself, outside skin, is a triangular shape. It's a triangular shape. And since we freezes the shape of the tower in a circular form, that will allow the architect to have a free form to keep twisting the tower facade to provide the spiral form for this building. This is outrigger. Now, I can jump through this very well. There's a lot of complex connection details to connect the super column with the trusses, and these are mega force. We're talking about hundreds of tons of forces into each connections. Now, this is a mega frame, the composite picture. It is a second line of seismic defense. The connections, I have to jump fast. The radial truss. Now, the floor framing is very simple. We have to keep it simple so the contractor can keep repeating the same construction process every week per floor. We have a core, which is concrete, very sturdy. They can do it by jump forming it. We standardize the formwork. They can keep jumping up. We standardize the size of the super column that's gently sloping up to form the tapering shape. And we have steel floor beams and then concrete slab or metal deck. They all come prefabricated in dimension shape. And we keep repeating it for each zone for different dimensions. This is a footprint. This is the podium space. And we have a seismic joint because when the building starts shaking, we don't want to shake it unsymmetrically with the podium. And also, we will have settlement joint as well, because when this building settles, we don't want to have uneven settlement. We want to make it settle evenly. So if it sinks, it will sink evenly. You see, we are keeping the floor plate in a circular shape, but the architectural feature is a triangular shape. We maintain it constantly up the building and make a different diameter as it goes up, and the architect has the freedom to express itself. This is a floor plate, and you can see all these are the struts that we tie back to the building. So when wind blow here, the forces will be transferred through this struts into the building. The vertical force of this curtain wall will be hung by the steel set rod, which we will see later on. All right, this is the mechanical floor. These are the details. This is the mechanical floor. We have full plate. We have full triangular shape. But the floors below it is only circular shape. Now, talking about the soil, we're going down the foundation are consisting of piles. The length of each pile we are using is almost 250 feet from the ground. We are driving piles all the way down to this dense silt sand layer with a total length of 70 to 80 meters, which is about 250 feet. We also have to have a slurry wall close to 1.2 meter thick. We have about 955 1-meter diameter pile underneath the tower. We have about 1,800 piles, cast-in-place ball pile, with 1 meter diameter or 700 diameter underneath the podium. Totally, we have almost 3,000 piles to support this tower. Now, this is the mat foundation itself. We have a tower mat supporting all the piles. Each dot is a pile. There's a slurry wall. The basement, we have 5 levels of basement, which is 25 meters below ground. And since the water table is so high, we're talking about 5,000 pounds per square foot of hydrostatic pressure uplift, okay, pressing against the slab of the last basement, 5,000 pounds per square foot. So how do we prevent the slab from bulging upward? We're using a lot of small 700 called anchor piles to anchor the slab back to the soil so it won't heave up. And for the tower, we don't have this uplift problem because the tower itself is tall and have enough mass to counteract the buoyancy. Now, we also try to use these thin walls and outriggers wall to distribute the entire weight of the building evenly to this mat foundation in order to distribute the pile to the load to this pile, so the building will have even settlement. So the mat foundation is about 20 foot thick below the pile. Just give you the order of magnitude of the massive scale of this project. And we are also using high-strength concrete as well. Foundation, give you some close-up. And this is the thin wall in the basement. We did a lot of computer simulation and hand calculation as well. Well, these are the loading we designed for different kinds of loading. This is a wind tunnel test. The building has a special shape. Not only we do regular wind tunnel tests like other tall buildings, we even spend hundreds of thousands of dollars to do a special wind tunnel test similar to the one they use for rockets and missiles in Canada. And this is how careful we have been engineering this building to ensure the safety. It's designed for 100-year storm. For strength, it's also designed for stiffness for 50-year storm. Also, when the building is so tall, people will feel the motion sickness when you are so tough. And different people have different perception to building motion. It is so-called acceleration. People always say, is the building moving very fast? No. It is not the velocity of the movement that makes you sick. It's the acceleration that will make you uncomfortable. Just like when you're sitting in an airplane, when the airplane is accelerating from 0 to 100 miles per hour or 300 miles per hour, you feel the jerk and the acceleration. When the plane is traveling at 600 miles per hour at 30,000 feet, you don't feel anything because the plane achieved a constant velocity already and you don't feel the acceleration. You are sitting comfortably drinking your martini. Now, but the building, you will feel it. If the building is moving, you feel the movement because you feel the building acceleration. And there's a guideline for that. And then when you are sleeping in the hotel, at the top of the building, the guideline for acceleration comfort level is even more stringent. There's approximately 15 millig. And for office, while you're working all the time, you don't feel the motion sickness that easily. That will allow you to have 25 millig. G is the center of, it's a gravity acceleration. Okay. In our building, because of our great design, we can achieve only 8 millig only versus the 25 millig. So we passed that comfort level. And for the typhoon, even with typhoon, we only have 5 millig versus the 15. So we can tell the owner that the design is quite efficient and achieve what they're looking for. Well, the owner said, no, it's not enough. We want it to be very, very safe that even some people who is very sensitive to motion will not get sick. So working with the two-mast temper, we have added a pendulum, which weighs about 1,500 pounds. At the top of the building, working as a swing. This thing is going to swing when the building activated. So when the building moves to the left, this may swing to the other side to counteract the movement in order to slow down the building, reduce the deflection, to enhance comfort level. It's a two-mast temper. Just like imagine you are sitting on a swing in the garden. You can swing your legs up, swing your leg down. That's how you achieve the motion. It's similar theory. When you want to slow down, you swing your leg in the opposite direction of the motion. That's how you slow it down. It is working in similar format. Well, this is some, we talk about the wind load. When the building does have the natural period, it reacts to wind. It's a natural frequency. For this building, we achieve, the building is symmetrical. It's very important. We have a very symmetrical building. They have a structural behavior that's symmetrical in both directions, the x-axis and the y-axis. So it's about 9 seconds and in the x-axis, and also approximately the same 9 seconds as the other direction. We also have torsion. The wind, there's a deflection of the building, is quite uniform. We also have a design for seismic. We have a small seismic, we have medium seismic, we occur every 60 years, recurrence, okay? You also have to design for medium earthquake that happens almost every 500 years. And this building, for the building code there, to make it ultra safe, we have to design for seismic event every 2,500. So I will move there if there's an earthquake. And not only that, they want to ensure that all lateral members can yield only in bending, but will not break. It will still be standing up. It will not be overstressed. So these are the requirements for earthquake. And we have done nonlinear dynamic analysis with different seismic curves. We have taken 7 seismic curves around the world, and each curve consists of X-Y axis direction that include the San Fernando earthquake and the Mexico City earthquake and a bunch of earthquakes. We went through more than 132 earthquake history experience and put it into our building to prove that it works. This is the simulation of earthquake. It has been magnified by 100 times, but don't be scared by that, just to show you how earthquake will work. I should not show it to the owner because he will scare him. Okay? But this is how a building behaves in real life. But you have to look at it with microscope. The building deflection on the top is only about 2 to 3 feet for the highest wind load. So this building is very stiff. All right, the crown, again, we have a beautiful crown for the architectural features. It's almost like 30-story deep. And curtain wall, again, Sergeant said, is twisting. You can see the building is twisting as it moves because you can see from the notches itself changes shape. But we maintain simple construction with a circular building-based building plate. It's a beautiful design. And you can see the curtain wall. Again, the building is twisting, but the building floor plate is not twisting. That is the trick. And we are hanging all these set rock, steel rod, 14-story to support the weight of the curtain wall brought back to the outrigger truss and the fin truss, and that create all this exciting atrium space. And this is a simulation of all that. And even when we detail all this curtain wall, we have slipping joints, slide bearing, all kinds of mechanism to make it work. The crown itself is also a very challenging cantilever things itself. So thank you so much.
Okay, so very quickly. The MEP engineers are usually the unsung partners in most projects, but I know that everybody today is much more interested in green design, high-performance design. So I'm particularly pleased that tonight we can also represent MEP engineering on this project with Doug Moss, who is the president of Cosentini Associates and the principal in charge of this project. Doug has over 30 years of experience in working with MEP engineering projects across the United States and then obviously internationally here as well. But I know that all of you are familiar with the 4 Times Square, which was the pioneering green skyscraper in New York. And Doug has also been in charge of the Battery Park City projects, such as the Solaire, which was the first residential green building in the U.S. And is down in Battery Park City in our territory. So I just want to share with you an observation that although lip service is always given by the architects and engineers to the team, if you were sitting down here with me while the 3 of them are chuckling about the project, you'll know that the real camaraderie develops out of projects such as this. So the third of the 3 amigos here.
Thank you. We're always last. People usually go to the restroom, take their cell phone calls, but I'm particularly pleased to be here, and this project has been a journey for us. I must say, I was just commenting to June. I think it was 4 years ago, 3.5, 4 years ago. I was at an ice cream parlor in Minnesota, and he called and he said, "We're going to be interviewed," and then the job was delayed a year. But a great project like this is really about collaboration and the big idea. And I have to give June a lot of credit because his vision for this building and the spiraling tower with the serpent-like enclosure really captured a lot of the sustainable ideas that will make the building great. And I just want to go through some of those ideas. And also to mention, our team is here. Chris Von Holt and Sam and a bunch of the people that have been dedicating their life for the last year for this project are in the audience today. We had a mission statement when we started the job, which is things that you're typically would see in any building: energy efficiency, resource energy consumption, building automation, high indoor air quality. But there were other challenges in Asia, particularly in Shanghai. One of them has to do, and I think Dennis mentioned it, you have to be able to build the building. You have to be able to get the products locally sourced. So suddenly we have a whole different way of looking at the building. We have to deal with local climate, local culture. The building is going to be a LEED Gold building and China 3-star And I think we actually have 36 base points for LEED Gold right now in the project. Now here's where the big idea comes in, and I think you've seen the basics from the architects and the structural engineer about the height of the building and the size of the building. But to me, what's really critical is when June called me and he said, we've got to build this huge, tall building, and we have to save energy, and we have to be good stewards of the environment. And what we really did is we didn't create a super tall building. We created stacked 15-story buildings. So as an MEP engineer, we looked at systems very sort of holistically, and we said the first thing we need to do if we want to build a great building is we have to reduce the load, the energy load in the building. And June created this jacket, this sort of external skin that goes in the building. And we said, great, well, this is like having another coat on the building. And we created a buffer zone that he discussed before. It's a buffer zone aesthetically, but it's also a buffer zone from an environmental standpoint. So what I can do in this cavity here, indoors, when you're inside the space, the temperature is it appropriate for an office space? And at the ground floor of the atrium as well, it's very, very comfortable. But the remaining part of the atrium space, we're using spill air because you're bringing outside air into a space. And rather than dumping it outside, we spill it into the atrium. So that buffer zone allowed us to create additional volume without using additional energy. The second part is to reduce the demand on a building. How do you reduce the demand load? And I'll show you some of the techniques that we use to reduce the size of the equipment and the capacity of the equipment. And the third part, which is really key to this project, is imagine if this building were laying on its side. And that's what we did. We said, if this is a horizontal building or community, what do? You run water, you run cooling, heating, power, and you connect to each building. So the only difference between this building and any community is we tilted it up on its end. And when you tilt it up on its end, we have issues of pressure, of hydrostatic pressure. So basically what we did is created little mini 15-story buildings with modular systems, very, very small mechanical systems that are in those mechanical areas. Now you say the mechanical areas, did I require them, or did Dennis or June? Well, they serve multiple purposes. One is structurally they're significant. Secondly, we need the refuge floor there for people to congregate. And third, it's a place I can house my equipment. So you'd be surprised if you look at the drawings, the equipment is standard size equipment, things that we can buy and we can service locally. During the competition, we presented this diagram. It's sort of hard to see, but it really was, I think, what was very important for us all. We went and we benchmarked energy consumption for Class A buildings around the world. And we took the top buildings in the world, not a B building, but the best buildings and state-of-the-art buildings. And the challenge that we were given is we need to have our building to be 25, 30% better than the best building. And in order to achieve that, we came up with some concepts. One is using this outer skin. I call it the triple glaze. And the second is the concept of a trigeneration, an electrical on-site utility that can make electricity, and we use the waste heat in the wintertime to heat and in the summer to cool. And by doing that, we were able to establish a goal. And I'm proud to say that through a lot of hard work among everybody, we are very, very close to that goal. We're about 24% lower than the code, and that's it's quite an achievement, because typically you go into a competition, you promise a lot, but the way things work, you don't get an opportunity to deliver it. And in this case, I'd say we're about 85% of where we thought we'd be, which is quite amazing. In terms of the energy efficiency measures that we took, lighting controls are very important, but the central plant, HVAC, and the envelope were the big contributors to the energy reduction in this building. And we used a number of techniques, which I think are very important. First is ice storage systems, and what that means is part of sustainable design is to minimize the resources from the utilities. And remember, this is the three siblings in this area. Can you imagine? You probably have 12 million square feet of office space in a tiny little location. You want to reduce the size of the electrical service coming there and the water. So we try to maximize the efficiency of the building. So what we did is we put a 27,000-ton ice storage system, and basically what that meant is at nighttime, when the cooling load's reduced, we run the chillers. We have dual-duty chillers, actually. We run them for normal temperatures during the day. At night, we make ice. We store it in tanks, and we use that during the day, which reduces the electrical demand. Tri-gen operating system, I meant this very simply. This is, we have generators that make electricity, and then we use cooling or heating, okay, in the different modes. And originally we had a much bigger tri-gen plant when we had more residential, but as the residential load reduced, the day-night balance changed. And we actually studied this ad nauseum. In fact, Chris ran all the studies on this, and we probably did 25 different tri-gen studies to get down to a simple payback of less than 4 years, and based on our return of investment in 11 years. So this, I think as Dennis said, these buildings are studied in detail, and we wanted to not just put a cogen, a tri-gen plan in to demonstrate something, but one that really makes sense, makes economic sense. The result of what I've mentioned to you in terms of the skin of the building, the ice storage, and the cogeneration allowed us to reduce a peak reduction of 30% of the installed load. So our chiller plants, all of the main utilities are 30% less than a Class A building would have been, and that was very important. It contributed. If you saw some of the diagrams that June had about greenhouse gas, we're using less greenhouse gas in this building as well by reduced demand and reduced consumption. We also have other requirements. China 3-star requires a geothermal system, and again, it's a relatively small geothermal system, but we put this in the building, and it's going to be serving some of the retail areas down below. Wind turbines. I think Dennis or June mentioned we have maybe 6 to 7 meters per second velocity. It's about 1,200, 1,400 feet per minute. And we have 150 kW of vertical axis wind turbines, and we're actually trying to fit more in there now, which will take care of the lighting and some of the other power requirements. Blackwater system. Again, if you have water, you might as well use it as many times as you can before you discharge it. And this gives you an idea that we're putting some blackwater systems to collect water from the hotel. We're going to process it on site, and we're going to use it for toilet flushing. So every element that we can reuse, we're trying to reuse and recycle. And I think between the blackwater and this should be a stormwater collection. Again, we don't have a big high roof, but we do have the high roof and we have the plaza. We capture that water, and you saw the diagram where we're saving the amount of water equal to 5 times the largest lake in Shanghai. So it saves a lot of water in the building as well. The location of the central plants. Again, we try to make it very simple. And just going back, if you heard what Dennis talked about, what June talked about, there really is nothing very complicated about the building other than the size. It's basic engineering principles we're using, and I think it's a lot of common sense. We have a central plant, cooling and heating plant in the basement, and we have another cooling plant on the 82nd, 83rd floor. Why are we doing this? Because of the pressures. If we put one plant on the top of the building, the hydrostatic pressure would be such that we can't buy local equipment and we can't maintain it. And this is the kind of building where in the future, if somebody puts a fan coil in or a water element in, we're not going to be concerned that there'll be a water break because the pressures are low. Again, this is to demonstrate that every 15 floors I have basically a pressure break. So it's a very low pressure system in the building. Electrical, again from the electrical distribution system, it's a horizontal utility tilted up on its end. We run high voltage up the building, we transform locally. So the transport energy, when you think of heating and cooling, we all think of refrigeration and we think of the heating and the boilers, but it's the fan systems are running all the time. Okay, so we want to have that transport energy, and if you look at ASHRAE and Lee, they talk about transport energy. It's extremely low because, again, we have these 15-story buildings that we're stacking. And again, electricity, I have switch stations up the building. A number of distributed transformers throughout the building. Okay. Again, you saw that very simple structural scheme that Dennis did for these belt trusses, which we're still working. We're getting a laugh here from my guys. Aren't going to be laughing, but when we tried to fit our equipment into these zones, we had to do this in 3D modeling in Revit. And we have fly-throughs of all the machine rooms, which I'm not going to show you now, but to show you the complexity of how you fit the elements in here. We have various zones of mechanical equipment, ran sections, and this is a tool that allows the contractors to understand the plans, because if you look at the plan, they're a 2D plan, and you see the equipment sitting there, and you say, well, everything should fit, but if you look in section, that's okay. But once you look in 3D, you understand that they're huge trusses. I think some of the cross braces are 3 meters deep. Air distribution system, again, key to the job, because we have a lot of office space. We have our very simple office space in the circular position, and we have a skin system on it, and we have a second skin on the outside, and that's my buffer zone that I use in the space. This is just another example of office distribution. If you look at the floor plans, everything's very, very simple. Very, very simple to build and to operate. Again, within this atrium space, we wanted to make sure we had enough comfort in there, and also if you're in the higher floor within a 15-story stack, you wanted to make sure that you have enough cooling to offset the heat stack. So what we did is we've run CFD modeling in the atria to determine the temperatures in the space so that people can be comfortable and we can predict what the temperatures will be. Smoke and fire, very, very critical in a facility like this. Again, when you realize if you're in the 120th floor, you may not be able to run right down the steps. So we want to have very safe systems. This is just a very quick depiction of, this is a machine room, and the brown is a typical office floor. And what this says, if there's a fire on an office floor, the office floor goes into smoke exhaust, and the atriums, which are circling the space, and the floors above are positively pressurized. So we're making sure the smoke does not escape from the floor. And then, we go backwards here. And if I have a fire condition in the atrium, I exhaust the atrium and I pressurize the smoke floors. But again, this is a 15-story building, so we have multiple 15-story stacks in this. I want to jump to something that is extremely important. You have a huge building, 5 million square feet, thousands of people, thousands of different systems going on and points, and how do you monitor all that? Traditionally, what we've been doing in the U.S. is we've been talking about, you have an integrated building management system, you have a security system, you have a fire alarm system, and there's a topic called IBMS, or Integrated Building Management Systems, utilizing Internet Protocol. And what that really does is it integrates all the systems that we talk about in the building. And I'll show you, and in addition to being the MEP engineers, we're also the security engineers and the technology engineers for this project. And this diagram, believe it or not, says it all. This basically is talking about a system architecture, which is sort of a Cisco type of system, where everything is going to be available in a Internet Protocol language. We have a telecommunication system, security, the BMS itself, which is what we call the temperature controls, the Johnson controls in Honeywell, fire alarm systems, the information networking, building management, building automation, hotel management, cashiering, all coming on the same platform. And you may say, well, why are we doing this? We understand that we're doing this from the standpoint of managing this, and that is because technology is going to continue to change in the future. And what we've done here is we've said there's two things that we have a responsibility for. One is making sure that we build a robust infrastructure. Cabling comes in. We have to have vertical highways, horizontal highways that we have redundancy, diversity, so that in 5 years, when this building is completed, or 6 years, when technology changes, that the infrastructure is in place. That's number one. Number two, staying on the IP protocol, we can have multiple manufacturers in non-proprietary systems that can achieve the goals of lower energy consumption, lower operating costs, and more responsive property management. And that really ties to two basic theories. One is the theory of we want to assess information, we want to know what's going on, we want to analyze it, we want to act. And the acting part is what we really hasn't happened in many of the high-rise buildings. We get the information, we analyze it, but there's no one source to act on this. And that's what the IBMS, I think, will bring to bear. And the other feature is, and I think there's a lot of words here, but this is the important one, future-proofing. We don't know what systems are going to be in the future. We don't know what technology is going to be, but as long as we create this highway, vertical and horizontal highway with the latest technologies, then we'll be safe in the future. That is the end. Thank you. I just wanted to stay within time.
Thank you all so much. We have 10 minutes maximum for questions, so if June and Dennis also come up onto the table in the front, and I can't really see anybody, but if anyone wants to shout out a question as we get organized, we'd be happy to entertain them. I know there are many engineers and architects in the audience, but anyone who has a simple question too about the building is welcome to ask it. So, expert or amateur? Anyone? Yeah.
Actually, the window cleaning actually is work with the same concept. You treat a big building as smaller buildings stack on top of each other. So at every 15 floors, the mechanical zones, there will be window washing machine. There will be track or window machine to be able to periodically from each zone where the mechanical floor is, the structure floor is. So you can have the machine go out to deal with each neighborhood, each zone. So will be zoned from each mechanical floor. The concept works the same. You treat a building as smaller buildings on top of each other. Not one big building, but 9 smaller buildings on top of each other. So it works everywhere.
You didn't speak about the glass skin itself. East, west, north, south. Is that going to be glass ones?
Yeah. First of all, the glass, the building we designed, basically you see is a triangular shape on the outside, which rotates continuously at the same speed, constant speed, all the way from bottom to top, 120 degrees. So there's not a true east side or west side or south side or north side. So there's not a true facade from one direction or other. But on the close to the western side, because in Shanghai, the most heat gain, the energy consumption is on the west side. So we studied overall the building envelope, and actually we put it into a simulation in terms of how the sun will affect the buildings. So from the energy saving standpoint, so we on the west side we probably were more heavier that we call the frit inside from the outlay of glass. So and on the south side, we create a horizontal wind shade, the sunshade, also the inside of the atrium space. So provide but mostly is west side. In Shanghai, in the winter time, in the summertime, the south sun is not as extremely problematic as the west side. So west side we will have a heavier fretting on the west side. The glass total we have about 2,000 pieces of panels in entire buildings, and each floor will have about 380 pieces of glasses. So because the spiraling, because the rotation, so the curtain wall the way we designed is to keep the glass on each floor is constant the same numbers, same size. Also, it's a very, very regular glass. It's not bent or anything. It's even in the construction standpoint, they're all vertical, plain, rectangular glass. So it's very easy to construct, and also for the future maintenance, it's very easy to organize the amount of glass. How can you keep the same panels on each floors? At this time, three of us, we supposed actually to finish our design development package right now, and we are going on to issue the tendering drawings for specifics down the road, like curtain walls and the structures. Structure probably already issued some of the tendering drawing already. So, and then we have our local design institute, which is Tongji University Design Institute, continue on the construction documentation drawings. Our design development package is still under reviews about government department and agencies, so get a final approval.
the construction standpoint, the basement, they basically finished all the pilings, and about 3,000 pilings always done, and they started the excavation already, and the building supposed to be the ground up about next year sometimes, probably around May, hopefully before May, which is a World Expo starts. Then then there probably will be 6 months duration during the World Expo in Shanghai. Construction probably will stop for a little while. Then the expectation of finish time will be year 2014.
How
I think maybe Dennis, you can talk about the structure system. What do we use?
Well, as I mentioned before, when we select the construction material, we pay special attention to the tower core, which has to be more fire resistant and impact resistant. In this building, we have a 1.2 meter thick, almost like more than 3.5 foot thick of concrete wall at the base, and it tapers up to almost about 3 foot thick concrete at the top. So it's very sturdy, both for earthquake requirement and stiffness requirement. At the same time, we also achieve a lot of impact resistance. For the super column itself, at the base is almost like 15 feet by 15 feet concrete columns, and with steel inside, the steel inside create ductility and elasticity for bending, and the sturdiness of the concrete provides the fireproofing and the stiffness for the tower. So it's very strong. I don't want to disclose anything that the owner would not want us to disclose, but we have been checking those elements for safety issues. For all the bell trusses and the radial trusses and outrigger trusses, since we designed for the 2,500 years earthquake, severe earthquake, it basically provides with a lot of strength, residual strength inside and redundancy inside. So to answer the question, it's very safe. And even the stair shaft itself, we're using concrete stair shaft. We're not using the drywall stair shaft. So again, there's another layer of protection as well. And we also have refuge floor every 15 story for mechanical space in the area, for fire refuge and for any accidental event that may happen. And I think mechanical engineers may have more to add.
And just when I mentioned the 15-story building stacked on top of one another, it literally is that, where we have there are very few shafts, other than maybe stairs and elevators, which actually penetrate the floors. We have pressurization systems in the building that are beyond a code, because we felt when we benchmarked this building against other buildings, and at the time we were designing, we were very, very concerned about, for example, there's no fuel oil being pumped up the building. We took all the steps that we felt were important, but from a smoke standpoint, if there's a fire in the building, it's about isolation. That's really the key on this building.
I think from the World Trade Center experience, we all learned in the industry that we always try to decentralize everything, even mechanically, structurally. So our building is like a module of every 15 floors, and even one section having difficulties, it will not cause any progressive collapse. We designed this building with progressive collapse restriction in mind, and that's another safety. So I think we do learn from previous experience and unhappy event, and we move on in a better way.
If I
Explain roughly how you distributed the liability between all the different parties?
What liability in China? We're not in the United States.
Liability if you don't finish on time, or if something goes wrong, or if the machine doesn't, if the building doesn't work right, or if you have a collapse because of an earthquake, or lots of liability. So how did you distribute the liability?
Basically, as an international architect, which is this, basically, I'll answer the question. We got all the fun, but we don't take any responsibilities. No. Basically, we work as international architects. Legally, we are as a design consultant, and but our design has to basically to meet all the China design criteria for the code, everything. So and we have to go through a very stringent process to get all various approved by the expert panel committee reviews, the government departments reviews. On top of that, the executive architect, which is a local design institute, which is also a Chinese government-owned design institute. They work for China government. They will take over as a final construction architect, executive architect to document and stamp the drawings. So that's how that works.
So,
basically, I mean, there are hundreds of examples. There could be a security breach. Someone could come into the stairway. There could be in the atrium, temperature zones may if I have a temperature rise in a certain area because of the sun is in a position, it may tell me to change certain mechanical parameters in the building. But I think the real goal of these systems, Panduit, Cisco, there are companies out there that are doing this integration, is about the future and creating the infrastructure to allow these algorithms to be written. So if you say give examples, you or I could come up with the same examples in this dynamic kind of building. But imagine a central 911 station that if someone gets sick, because there'll be thousands of people in this building, or if a diffuser, someone's cold in their space, or the toilet gets clogged. I mean, something that basic, it all comes to a central dispatch. And our job is to create the avenues and the streets to allow this to present itself in the next 4 to 5 years. So that's really what this is about.
okay. So we don't end on something too mundane like the toilets. Let me just conclude with a final question, because we did talk about symbolism, we talked about economy, and we talked about height. And I wonder if you could comment, any or all of you, on the question of the tallest building in China, the competition with standing on the world stage through height, through the symbolism of a new kind of building. Economy, Dennis, you mentioned, was incredibly important, but what is it about the building and its height that you see as something which is symbolic, not just a machine for creating money or a machine for processing water and air?
I'll probably take a lead on answer, and maybe you guys can add on. I think, first of all, the idea to build this building is really how the building architecture can really connect to the communities. I think that's the most important thing, is for that building to be the way we design it. That's how we approach the design. So the building, from the geometric to the architectural concept about a neighborhood, so actually be very transparent, very public accessible. Although today everybody talk about terrorists, or everybody coming in as securities. Everybody's trying to be insecure. If you're insecure, be defending yourself, nobody can touch it. But when we design this building, we want to make this building open as a public, because this building is going to be working with many people working there. But China is a very open now, engaging society today. The building will get millions of people to come in to see the buildings and to work in there. So the idea is to create a community is open, transparent, and accessible, and engaging. So from the geometry itself, it's very dynamic, it's very soft, it's very transparent, because you use double layer glass. I will talk about the outside the glass. I didn't mention about in the presentation. The outside glass is going to be the clear double layer that sandwich the glass. So actually, it's be very easy to see what's going on inside. So the public gardens will be very visually be accessible and also physically accessible for people. So that's most important, is with
building is built for the people in Shanghai. It's a vertical community, vertical cities. People can experience and enjoy it. And so that's we think from the metaphor standpoint, from the meaning standpoint, it's important. In the meantime, it's a sustainable building. So which one show example for a tall building like that. We can build a very sustainable buildings. The reason we divided this very many zones, the other reason is we try to create a more convenient lifestyle for people. So people if you walk the one zone, you don't have to go down to the base of the building waiting for elevators ever to go to have a coffees or get a sandwich or go to banks in the lunch times. So each zones you could create those amenities. So for people to go there to have a basic support for your lifestyle, Also, you save lots of energy for elevatoring in that way too. So the design is to design this for a very livable communities, but you stack it vertically. But that's the idea.
Should we let the architect have the last word in this case? And thank you all for the evening. Thank you so much for a really fascinating presentation.
Thank you very much.
Thank you, everybody.